Imagine you are standing on the observation deck of one of the tallest buildings in the world. You feel something strange under your feet. Not an earthquake, not construction work. The building itself is moving, just slightly, just enough that your stomach notices before your brain does. You look around. Nobody else seems worried. The tour guide keeps talking, and a question forms in your head. Feels almost silly to ask out loud. Why isn't this building falling over? Most people assume the answer is simple. Thick steel, deep foundations. Strong concrete? Just build it tough enough and it stays still. But that is not what is actually happening up there. The real answer is stranger than that. And it is sitting quietly inside the building's core, doing something that looks less like engineering and more like a magic trick. And once you understand what it is, you will never look at a tall building the same way again. Because the last part of this is not really about skyscrapers at all. It is about the price of stability and how far we go too. Hide the wobble underneath everything that looks solid. Let's start with the obvious problem. Wind. A tall building is not a rigid rod stuck in the ground. It is closer to a very tall, very heavy tree. Wind pushes against its surface, and the building bends. Not visibly to your eye, but measurably. Engineers call this sway, and in a super tall building, it can be several feet at the very top on a windy day. That sounds small compared to the height of the building. The problem is not the size of the sway. The problem is the rhythm. Every tall structure has something called a natural frequency, a rhythm it wants to swing at. The same way a wine glass wants to vibrate at a specific pitch. If wind gusts happen to push the building at a rhythm close to that natural frequency, the sway does not stay small. It builds. Each gust adds a little more energy to the same motion. The same way pushing a swing at just the right moment sends it higher and higher. Engineers call this resonance, and left unchecked, resonance can turn a light breeze into a serious structural problem over time, not because the wind is strong, but because it keeps hitting the same rhythm again and again. Now imagine you are the engineer responsible for this building. You cannot make the structure infinitely stiff. Stiffer materials cost more, way more. And past a certain point, they do not solve the resonance problem anyway. They just shift it to a different frequency. You need something smarter. You need something that fights the building's own rhythm from the inside. This is where it gets strange, because the solution used in many of the world's tallest buildings is not more steel. It is a wrecking ball, a massive steel or concrete sphere, sometimes weighing over 600 tons. Suspended near the top of the building on cables and springs, hanging almost free, like a giant pendulum. It is called a tuned mass damper, and what it does sounds almost too simple to be real. When the building sways one way, the ball, because of its own momentum, lags behind and swings the other way. It pushes back against the building's motion at almost exactly the wrong moment for the sway to continue building. The building's energy, instead of compounding gust after gust, gets absorbed and canceled by hundreds of tons of steel, quietly swinging in the opposite direction. The most famous example sits inside Taipei 101, once the tallest building on Earth. Near the top, visible to tourists through a viewing window, hangs a bright yellow steel sphere weighing roughly 660 tons. Built specifically to counter the sway caused by the powerful typhoons that regularly hit the region on a strong storm day. You can actually watch it move, inches at a time, quietly doing a job most visitors never think to ask about. You've already encountered this principle when you drove a car on a bumpy road, and you felt how the suspension cushioned the impact instead of throwing you up to the ceiling. You felt the damper at work. The energy was redirected and dissipated rather than being transferred directly to you. Skyscrapers just do the same thing at a scale most of us never imagined standing inside. But here is where the story gets darker, because getting this calculation wrong has actually pushed a real building to the edge of collapse. In 1978, an engineering professor named William Lemaitre, the structural designer of the CD Corp Center in New York, one of the tallest buildings in the city at the time, received a call from a student who had been studying the tower's design. The student pointed out something about how the building's wind bracing had been altered during construction, bolted joints instead of welded ones. To save money, Lemaitre ran the numbers again himself and reached a conclusion that turned his stomach. Under the right combination of quartering winds hitting the building at an angle rather than head-on, the joints could fail, and a major storm capable of triggering that failure hit New York roughly once every 16 years statistically. The building he had designed, occupied by thousands of people daily, was at real risk of collapse? Was one of the few systems actually functioning as intended that entire time? Buying critical stability while the real fix was welded into place in secret. That case reveals the deeper layer underneath all of this. A tall building is never a finished, static object. It is a structure in constant negotiation with forces trying to push it out of rhythm. And every safety margin engineers build in exists because somewhere, someone ran the numbers on what happens when that negotiation goes wrong. The wobble you might feel standing at the top of a skyscraper is not a flaw. It is proof the building is doing exactly what it was designed to do, bending instead of breaking, and quietly fighting its own resonance thousands of times a day, so you never have to think about it. Not every tall building needs a tuned mass damper. Shorter towers, or ones with a wider, stockier shape, often have a natural frequency far enough from typical wind gust rhythms that the risk of dangerous resonance is low. It is specifically the very tall, very slender buildings, the ones that look most impressive on a skyline, that need this hidden countermeasure the most. The taller and thinner the structure, the more it behaves like that wine glass waiting to find its pitch, and the more it needs something swinging quietly against it to stay in tune. So now picture yourself back on that observation deck, feeling that same faint sway under your feet. It is not the building failing to stand still. It is hundreds of tons of steel, hidden somewhere above your head, swinging gently in the opposite direction of the wind, absorbing an invisible fight so you never feel the worst of it. The stillness you expect from a solid structure was never really stillness at all. It was balance, engineered, tested, and in at least one case, corrected in secret at the last possible moment. And that is the real lesson hanging inside these buildings. The things that feel the most solid are often the ones working the hardest, invisibly, just to stay standing still.